When we were back in the good old days, we were doing two dimensions. We could just talk about tangent lines. We could just get, like at this x value, we get the tangent line at that x value. Remember talking about, okay, so the tangent line's pretty good at that point because around that point, the tangent line and the function itself, they're nearly indistinguishable, okay? Well, when you get to 3 dimensions, of course, tangent lines, you got all kinds of tangent lines you could draw for a particular point. But what we'll talk about now, though, is a tangent plane. And so when we've got this, let me try to draw what I've got on my paper here. So we've got this surface, and that's kind of a bowl kind of shape. I guess that's what I was going for there. So if I've got this function, z equals f of x, y, whatever shape, I mean, it can be quite a complicated shape. What I can talk about is, I get tangent lines in particular ways there, but what I can talk about is, say if I pick a point, and I don't know what the best, I picked kind of one, maybe, I think the one I picked is kind of on the bottom side here. What you can talk about at that particular point, which they'll call x0, y0, z0. You can talk about a tangent plane at that particular point. Tangent plane. So coming up with a plane that's like I said, this is kind of on the back side there. It's kind of hard for me to draw. Kind of harder to draw a mathematician like myself. But you get the idea. And the thing about that is there's a lot of analogies for that to what we're talking about here with the tangent line in 2 dimensions. Because between the curve and the tangent plane then, that tangent plane is indistinguishable in around that point. So it mimics that for that particular little part. Now, of course, the further away you get from that point, it doesn't do a very good job of giving you function, doing the function there. But anyway, that's what we're talking about. So how do we find these tangent planes? Well, let's recall here. So if I've got a point, so this is the tangent plane at that x0. x0, y0, z0. Well, if I want a plane, just any old plane, for a point, x0, y0, z0, let's use that. The other thing we would need is that normal vector, and that's not what we're going to use here, but that's the way we did it before. So let's just call it ABC normal vector. So we got that perpendicular vector to whatever plane we were trying to make. Well, turns out we're not going to actually have to use a normal vector for these tangent planes because of what we know about tangents. That's good news, okay? But if we've got those 2 bits of information, then the plane is just a times x minus x0, b times y minus y0, plus c times z minus z0 equals 0. Well, the way they usually describe these tangent planes, or the way we'll find these tangent planes is actually what I'm going to do with this is I'm going to solve it for z minus z0. That's how we're going to kind of give the formula for this tangent plane. All right, so that would mean moving these terms over there. So we would subtract a times x minus x0, subtract b times y minus y0, and then divide off by c. So we get z minus z0 equals -8. Let's write it this way. Okay, so that's still not what we're going to use here because you know, A and C are off this normal vector. Like I said, we're not going to have to use that for these tangent planes. I mean, we're just trying to find a plane in general, but we're talking tangent planes. Well, let's clean this up a little bit. Let's just rename this as just A, and this just little a, and then this little b. Okay, all right. Well, all right, so if we think about, so this in a way is our plane. I want it to be a tangent plane. And so if I take this right here, whatever it is, hypothetically whatever it is, if I intersect that with this y equals y0 plane, in other words, y equals y0. That, since y equals y0, y equals y0, isn't that 0 right there? So we just wind up with z minus z0 equals a times x minus x0. And remember that intersection with you know, the plane that y equals this given point, that's the tangent line. The slope of the tangent is the tangent line to, you know, the curve. We're talking about a function here. So the intersection, that gives me a tangent line. And what do I know about the tangent line that intersects this y equals y0 plane? In other words, y equals this value. The slope of that is the partial with respect to x. So a here is the partial with respect to x at my x0, y0 point. That's what a is. We don't have to mess with that normal stuff because, you know, finding that can sometimes be fun in and of itself. Because of the very nature of what we're doing here for this tangent plane, this is the partial of x, partial of f with respect to x. Well, guess what b is? Similarly, b is going to be the partial of f with respect to y at x, y, x0, y0. So here's the story. The tangent plane at x0, well, yeah. So the tangent plane for z equals f of xy at P, point P, x0, y0, z0, is z minus z0 equals A is the f, partial of f with respect to x at x0, y0, times x minus x0, plus partial of f with respect to y at x0, y0, times y minus y0. Yeah, so to get the tangent plane, yeah, I mean, it's similar to what we would do if we were trying to find the tangent line. Remember, if you're trying to find the tangent line of just a two-dimensional curve, the derivative is the slope, right? Sort of the same thing here, except you've got the complication that you have two partial derivatives. And it also resembles the point slope form of a line, right? Y minus y0 equals m times x minus x0. So this is just, we've just extended it to 3 dimensions, I guess, if you will. Okay. So, not it's really, I mean, the formula looks long and complicated, but really it's pretty nice. So let's find the tangent plane. For z equals 2x squared plus b squared at the point 1, 1, 3. So we just have to fill in the parts here. Of course, this is our x0, y0, z0 point. So it's going to be, really the only thing to compute here then are these two things. So what would be the partial here with respect to x? That'll just be 4x, wouldn't it? Y is fixed, so this is 4x. And we want it at x0, y0, so we're just going to compute that at 1, 1, which makes it easy. X is 1, y is 1, but we just need x anyway here, so this would be, for this one, just 4. The other one is the partial of f with respect to y, x0, y0, so the partial of f with respect to y would be 2y, and so that evaluated at the 1, 1 would be 2. And so then, the tangent plane, we got z minus z0, that's 3, equals this, which we found out to be 4, times x minus x0, so that's minus 1, plus then that, which we found to be 2 here in this case, times y minus 1. Ta-da, okay. So for a tangent plane, it's fairly straightforward. Now, usually what they do is listed in z equals form. Yeah. So let's solve this for z and simplify here. So that'd be, well, let's go ahead and distribute. 4x minus 4 plus 2y minus 2. Yeah, so just add the 3. Solve for z, so it'll be 4x plus 2y minus 3. Not too bad, right?